Well, the first thing we needed to do is figure out where is the telescope pointing relative to the spacecraft. So we waited for the near-infrared camera to get the detectors cold enough so that we could take images, and we did some evaluation of that. And once we were convinced that it could take images, we were really trying to determine if we pointed at a bright isolated star, where's the telescope pointing? So we picked a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned yet, so so they actually act like 18 separate telescopes, and we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star, and we made a mosaic. We actually took the near-infrared camera and we took images in different parts of the sky, and then we looked for the 18 spots from the 18 different telescopes, if you will, and we were very excited to find them. They were actually very close to where we were pointing, well within our expected size of where they might land. And the 18 spots were actually fairly close to each other as well. So really everything was very close to what was predicted and much better than what we considered to be the worst case pointing. So we were really excited about that. We also took a selfie of the primary mirror. We took an image of the primary mirror, and that helps us understand the alignment of the telescope, especially the primary mirror, to the camera itself and the instruments. And initially that looked good as well. So far, the data we have suggests that what we're seeing matches between our models and the actual data. We're just getting going, but we have now gotten some data looking through focus, and we've been able to see that we don't see any surprises in the shapes of the mirrors that we're looking at. So far so good, but we do have a long way to go. We've also now identified which of the 18 spots is which mirror. And we've done that through a special process that allows us to identify them. And at this point, we even know which ones are from the wings. And it turns out one of the wings, you can actually see those 3 spots are a little farther over. And that's sort of what we expected. So we've identified all 18 spots, and the next step is to make an array of them. And then we're ready to start what we call global alignment, which is when each of those 18 spots will start to be aligned and focused. And that's sort of the last step before we take those 18 spots and put them on top of each other to start forming a single star from the single star going through the 18 separate telescopes. And that's the work that we'll be starting soon. What the selfie is there's actually a special lens in the near-infrared camera that you can put in, and it allows you to take a picture of the primary mirror itself. And in this particular case, one of the segments is pointing at a star, so that is the segment that lights up. But you can see the outline through the shadows of all 18 segments, and you also can see the outline of what's inside of the instrument itself, and we can see how well that primary mirror and the telescope is aligned to the instrument. And that gives us some initial confidence that the alignment looks good, and that's a good starting point for doing the alignment of the telescope. The first evaluation images actually came in the middle of the night, and that was just to determine whether the near-infrared camera was working well enough for us to start the alignment. And the NearCam team, the near-infrared camera team, and the telescope team got together the next morning and looked at the data, and everybody was happy that the camera was working well enough. So then we pointed the telescope at this bright isolated star, and we started taking the mosaic where we would look at these different places in the sky. And when we pointed the NearCam at one particular point pretty early on, we saw 9 of the segments in that one image. And everybody basically broke into cheer because we were so happy. It meant that we had figured out where the telescope was pointing, things were working right, and even the spots themselves looked like what we had modeled and what we had expected. So there was, people were very happy about that. And then we've also been evaluating the data as we go. We did this thing called a focus sweep where we looked at the images through focus, and we've been evaluating those in detail. And at this point, as well as we can evaluate them, things are matching our models. And so there is a feeling right now that things are consistent with what we predicted they would be and what the model said they should be. And that's all you can ask for as you start a process like this. One of the great spin-offs from the James Webb Space Telescope was when we were developing the mirrors. We actually developed a technology. We funded a small company to develop a technology that could measure the mirrors at an earlier state. It's a device that was called a scanning Shack-Hartman sensor, which is a complicated way of being able, saying that you build something that can measure a mirror that has a lot of curvature early on while you're initially grinding and polishing the mirror. But that company actually got bought by a larger biomedical company in order to use this sensor as part of a system that can do LASIK eye surgery. It has the ability to measure astigmatism in the eye, and so it became part of a larger biomedical company. But the investment in the technology that we did for James Webb led directly to that technology then being part of this future spin-off. Yeah, I actually am legally blind in my left eye. It's one of the reasons I got involved in optics. I have like 2,500 vision in one eye, and as I was growing up, I was always very interested in understanding how I could do depth perception and how the eye worked, and whether there was a way that I could, do something to help my eye. And so it just got me interested in optics. It's one of the reasons I studied optics. And there's definitely overlap between ophthalmology and how you deal with eyes and how you deal with telescopes. And one of the real interesting ones is you have a pupil in your eye. Well, in a telescope, the primary mirror is the pupil. That's the pupil of the system. They're related by optics. And so we use a lot of similar things. And I feel like I've kind of gone back to the original reason I got interested in optics and thinking about how it relates to the eye.